Hello, hello. Hello. All right, everyone. How's everyone doing? Not that there's many people here, but hey, just grabbing the chats. So, right, we have the chat here. Now I need the chat on YouTube as well. There it is. Now I need the. We can close that. There. And let's just tile these. Cool. So we have YouTube chat. We have Twitch chat. I will be checking these periodically. Let me know if. Yeah. All right. Let's get started. So, what are we doing today? Last time on the stream, we were doing some Dijkstra stuff, and we actually got it working. We finished the stream on quite a nice high. We have this little test case that tests, point A to point B. Yeah, and it does pretty well. I want to do one more test case just to make sure there's no edge cases I missed, no flukes. And the other thing that we need to do is to actually use a priority queue here. So last time I tried, I failed, and I ended up using an array list. But obviously this is not good because it increased the complexity of the algorithm to be quadratic instead of n log n. I think that's correct. Yeah, it's a little bit more complicated, the time complexity for graph algorithms, because you have to account for edges and nodes. No, sorry, edges and vertices. That's the correct terminology. Yeah, and we just all we did was literally we went on Wikipedia. I googled Dijkstra's, saw the pseudocode and implemented it. So you need. It's a good skill to have. Just being able to look at like pseudocode, English type stuff, and being able to just implement it yourself. What about data structures? Well, we have an overall graph which contains nodes, which is an array of pointers to certain nodes. One thing I don't really like about this is that we have this work distance on the node level, which isn't great, because it's then used to kind of mutate as we go along, and yeah, we're kind of storing some stuff here that maybe shouldn't be here. But I'll leave it for now, because it could be like a private field or something like that, and it's quite efficient to store it on the node level instead of on another data structure. At least you have very fast lookups. Yeah. Anything on the chat? Nothing on the chat. How many viewers? We have one viewer, which is me, and here we have one viewer who is also me. Yeah, never quite sure what to say when I'm just alone. This is also, going on the VODs. So, all right, let's continue. So, how do I spell Dijkstra? Dijkstra's algorithm. Test cases. Shortest reach hacker rank. No, that's too small. I guess we could draw one. We could always draw a graph. Something like this. There we go. So I'm just going to use the mouse. I do have a drawing tablet, but actually, no, let's just use drawing tablet. You guys can't hear it, but my dog Simba is really going for it. Let's have a stream for him. Simba, come here. Simba. He's shy. Okay, so we have a graph, start and end. Let's say you just have kind of 3 nodes like this, one like this, one like this, one like this, should be enough. So this goes here, this can go here, or there. This can go here, here, and here. Let's make it even more complicated by this one going there, this one going there, this one going there. This one going here and here. And let's make the real path. Let's kind of, I think this is nice. This to this to this to this to this. Yeah, that looks good. So to make that the best path, let's make it orange for the weights. No, that's not quite orange. Give me a good orange. Yeah, that's okay. Let's make you 4. Let's make this 3. Let's make this 1. Let's go 5 and then 4. So then this here could be 6. If there is 6, that would add up to 10. This that means that the shortest distance is 4 plus 3, 7, plus 1, 8, plus 5, 13, plus 4, 17. 17 is kind of the number to beat. So this up here would give you 10, so we need to make this 8 to make that top 118. The bottom one would also have to be quite a bit because we need to make it at least 13. So let's make this 10 and then make this 4 as well. So we have some extra edge cases. And let's... yeah, let's add just one extra that goes into there. Just, you know. Let's go, what should that one be? So 4 plus 3, 7, plus 10, plus 4. Well, it can be literally anything. Let's make it 1, and it will still be way too long. Am I missing anything? Oh, I'm missing these 2 weights on these 2 edges. So 4, 3, 1, that's 8. And then 8 plus 6, 14. It has to be bigger than or equal to 3. Let's make it 4. And then 4 plus 8, 12 going down, and then the 4, 16, it just has to be 2, right? So 4 plus 8, 12, plus 2, 14, plus 4, 18. So this can be 2. Okay, we're all good. Let's just put this in one of our test cases, make sure it still works, and then let's refactor it so that we have a priority queue instead of just an array list. And then, yeah, and then we're done. We can't really do much else. And then we can actually solve the out of code problem that I am implementing this for. All right, let's go. Okay. So test bigger graph. Let's just copy some of that. Bring this down here. Let's label them as well. What should we do that in? Let's do that in purple. So you're A, B, C, D, E, F, G, and H. A, C, D, E, F, G, and H. That's it, right? Yeah. D, E, F, G, H. What's this? Oh, it's unused, yeah. So we need an A to B, an A to D. Oh, that's so many things to look at. It's actually... Oh, God, where am I? Yeah. Let's just put you over here. Zoom out, and then let's just shrink this. Okay. So we can see everything. So we need an A to B, an A to D, a B to F, a B to C. Let's make spaces on the root node. B to C. Then we have an A to D. Let's go from C to E, C to D. Yep. and then a D to G. D is done, so we can have E now, E to F, and then we have E to G. Then we can have F to G and F to H. And then the last one is going to be G, and there is just a G to H. Okay. A lot of stuff. Alright, good. We can put you back over here. We can bring this back up. Okay. Oh, we don't put the distances. Forgot about that. Alright, let's bring everything back. Okay, the distance A to B is 4. A is 4, B to F is 8. B to C is 3. C to E is 1. C to D is 1. D to G is 10. E to F is 4. E to G is 5. F to G is 2. F to H is 6. And then G to H is 4. Cool. I think that's everything, hopefully. Let's just count 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're all good, we're all good. Okay. In nodes, there is a D instead. B, F, C, C, E, D, and G. What is that? Okay. Replace with an E. Replace with E. Find the ampersand. Go one to the right. Replace with F. Replace with G. Do that. Replace with F. Replace with F. Replace with G. Replace with H. H. G. Okay. Cool. Let's do the nodes now. E, F. We see the E, F, G, and H. That counts for those. And then the graph is that. Wait, where did they go? Oh, yeah, I need these, don't I? A dot out edges, A, D. B dot out edges, B, F, B, C. C dot out edges, C, E, C, D. B, C, C, E, C, D, that's it. The D out edges, this D, G, E, F, G. E, F, E, G, F, G, F, H, G, H. I think we're all good. Shortest path from A to H. We calculated it and it was 17, was it not? Yeah. Okay. Let's see. And it is. It all works. Feed testing with a harder graph. Okay, now we have two baselines, one easier, one slightly more difficult. But it all works. Now we're just gonna have to change it to be a heap, a priority queue, implemented with a heap. Oh, hello. We got two people here. Hello, I'm currently learning Android development. Some advice for Kotlin. I've done Java, so suggest me fastest ways to do Kotlin and tell me what should be the first thing I should learn in Android dev. So Android development's kind of a funny one. because of the mix of languages, and there's a lot of versions, and mobile development in general is just quite difficult. Honestly, if you know Java very well, then just understanding Kotlin very well will basically head start you a lot. So what I'm doing right now is doing some more Advent of Code problems. Adventofcode.com is a really good way to get familiar with syntax and stuff that you're unfamiliar with. So if you're just learning the syntax, then doing Advent of Code in Kotlin will be good. You should be able to do most of them, to be honest. As for any advice, I would probably get somewhat good at doing UI. Because obviously apps are very visual. That's it. I would say just get good at the language, get a little bit of UI, and just do projects. Just make an app. Just do it. Even if it's terrible, you'll gain the experience. Hey, do you have any idea of DSA using C++? Solve the problems doing C++? I'm not sure that's actually the best advice, to be honest. Yeah, but I want to start creating projects. I don't have any idea how to start. C++ is a huge... you're kind of really putting yourself in the deep end there. If you don't know any other programming language, then C++ is going to be very difficult to start with. It's really not like beginner friendly at all. If that's the case, then I actually really recommend you learn Go. And the reason is it's very fast, like to compile, so you have very, very fast response times and stuff like that. And second, the syntax is very, very simple, but it's able to introduce you to type-safe compiled languages, which C++ is. It also can do pointers and stuff, so you're kind of, learning a little bit about that as well. But it's just super simple. So if you don't know how to program, I actually really recommend you start with Go. Very, very simple programs. You don't have to do anything with Go routines, none of that. Just use the type safety that it provides. Just use the types of compiler, and you'll be good. You'll be good to start learning with this. As for C++ specific advice, well, I think you're actually asking the wrong person, to be honest. But I am doing Zig, which is not similar to C++, but it's the same realm. Memory managed, pointers, kind of unsafe languages. Well, unsafe, kind of. And honestly, same advice as for the other guy. Advent of Code. Advent of Code, most of the problems after 6, 7, will require a really good understanding of data structures and algorithms, especially data structures. So what we're doing right now is we're solving for problem 17, which requires a really good understanding of graphs, which is what we implemented here with these data structures. Not just graphs, but the algorithm to do the shortest path through a graph, Dijkstra's. And the ability to implement Dijkstra's from just looking at this. Like this function here, I just went on Google and type in Wikipedia Dijkstra's. I looked at the pseudocode, and from here I'm able to implement it. Now, Dijkstra's is not the most straightforward algorithm to implement. It's a little bit harder. So you might want to start with something more simple, some of the more simpler algorithms. So like stuff like linear time median, maybe. What's even simpler? Honestly, just understanding trees, tree search, traversals, binary search from scratch, that type of stuff. Really invaluable. It's really good. Yeah, but starting projects with C++, you're really throwing yourself in the deep end there. So, to be honest, I'd consider trying something else a bit easier if you're still new to programming. If you're really adamant on C++, I'm actually not sure. I've never used C++. So I would just say get good at the language. Do some Advent of Code problems. Just all you need is a compiler, right? I'm pretty sure every machine has GCC installed, basically. So you can just GCC whatever your C++ code is. Yeah. Thanks for joining, guys. I do appreciate it. I'm not sure when these messages were, so maybe I just talked to no one. But still, I think it's pretty good advice no matter what. Cool. Let's continue. Test passed, so now I have to implement stuff using the priority queue. Okay. because I'm going work queue. Okay. Var and priority queue equals stand dot priority queue, which is of type const node. This context, I think I'm just still so unsure about. But let's have a look at the test cases again. So I think context less than can be void if these are then the types. I mean, maybe I can just do void. I think it might be able to do void. Yeah, let's do void. Comtime compare function compare nodes, which takes in two constant pointers, A and B, constant node, and it returns standard dot order. Is that right? What do you have over here? Order. Order is standard dot math dot order. Oh, right, sorry there. Don't need this. There we go. And then we're just going to return whether A. Oh, and it's context type void. A dot work distance. We want the shortest, so actually we want to do over here. Not math. Oh yeah, I can just do standard dot math dot order B dot work distance, A dot work distance. We want to do it the other way around because we want to find the minimum, not the max. So then down here we go compare underscore nodes. And what else do we need? From a priority queue, A and B. So we get two types less than. Oh, A and B for the. Oh yeah, that's it then. Okay, priority queue. Cool. Unused function parameter. Yeah. Priority queue. Let's turn that into work queue. Is it still append? No, it's dot add. Dot add. I do, because what I need to do is I need to go work queue dot d, no, not the init. I need to also dot init with the allocator. That's it. Dots removes and returns the highest priority queue element. But to remove just does this. Whereas, wait, remove index. We have an assert. Last item removed, nothing else to do. If index is 0, sift down. Sift down, return item. So we're sifting down on remove. Yeah. I think this makes sense. Yeah, so it's kind of it sifts down when you remove, so then we don't really have the problem of updating the work distance outside of it. Okay. Closest node index. Can I just, maybe I can just do this. Closest node, any type errors, let's test. Okay, doesn't like it. Expected 2 arguments, find 1. Well, what does it want here? Let's look again at the implementation. What about when context is really not needed? Oh, I just give it, wait, what? Empty object? It's kind of funny. Just, does that work? Didn't even know that was real syntax. Okay, what is this? What is this? Okay, test can find. No, can find. No. Oh, hello. This is a pretty sweet new Neovim config. Is it custom? Well, first of all, thank you for joining. It kind of. It's a little bit custom. It's not really. It's NVChad, but with a little bit of configuration by my side. So I just find that like NVChad gives you such a good starting point, and it doesn't force you to update, and all the Lua files are there, so you can do whatever you want. No, it's basically this. You can see it's so similar. I left most of the defaults on and just installed plugins I needed. Yeah, it's NVChad, nvchad.com. And the theme is Everblush, that one. Yeah, it's pretty cool. I don't think I need I do kind of want to do a custom one, but I find this one so good that, you know, what's the point? But I might just do it for fun, maybe on stream. Okay. I actually need to know Zig test specific case. Zig test from single case. This is a thing. Just brainstorming here. Is that actually no command line? It's complicated, by the way, because you can use any literal in the test name, not just string literals. Test rework or filtering works? -- test filter. Okay, well, that just doesn't seem to want to work then. Let's just comment stuff out. -- help. Hold on. Oh wow, you are. Okay, it does have test - filter. So test - filter as can find. Okay, so that top one passes, but not the bottom one, which is interesting. Bigger graph. Oh, biffer graph. Bigger graph. Interesting. Expect _ equal. Let's do that. Equal. Expect equal. Because if we do this, then we should be able to see what the left and right is. Wait, what? Oh, I changed the wrong. Yeah, whoops. There we go. That's correct now. Oh, still not telling me what it is. That's annoying. A to H. Because the funny thing is, well, it just worked just now, so has to be something going on with the work distances, I'd imagine. Okay, let's print. Let's print shortest, just say H, there we go. Let's test. 18. It did 18. Yeah, 18 isn't correct. Thanks, I gotta try that. Yeah, no worries. 18. Interesting. 18. Get rid of that comment now. Set them all there. DQ. Okay. Print closest node. And let's go closest node dot label. let's test. Oh, I need to do the this isn't a slice. Okay, first node A, B, C, D, G, F, H, E, D. Okay, let's get GIMP back. So it goes A, yeah, that's correct, and then it goes B, and then from B it goes C, and then it goes G. Yeah, that's not right. It can't go G because my man, there is really nothing there. Okay. Do you wonder how it did that? I mean, the remove code itself.remove. Does the last item, the current item that I'm trying to remove? I'm trying to remove 0. Self item at index, which is going to be 0, is equal to the last item. Okay, so the work distances does cause a problem. Because I'm updating. Yeah, you see here, I'm updating work distances, but the priority queue doesn't really know that, and so doesn't do anything. So I need to, is there like a rebalance? Queue dot updates. Yes, there is. And what is this update function? Updates 55. Okay, the item. Oh, it's going to do equality check. Compare function. Wait. There, it tries to find the index. Does I plus 1 equal to 1? The item at the index. If the item and the element that you're searching for is equal, then you break. You break the statements. You go back down. The old element, update index. Maybe there's is there an update? Update after remove. Okay, well, updates. Oh, that's not always going to be correct if it looks for. Yeah, I don't know if this works, but let's try it. I feel like this might not work. Let's update the neighbor. Well, we want to update it with itself, but maybe, is that like, can I just call sift? No, shrink and free. What are the methods we have? So we have remove, init, add, neighbor is equal to edge.out node. And slice capacity iterate remove index, remove and return element at index. Remove on null, ensure total capacity from slice cap. Okay. So I can't really do that one. There is remove the highest item. Yeah, that's what it's for. It's kind of interesting here because we know we have neighbor, and we know we want to update neighbor. We want to update it with itself. Okay, this seems weird, this line. Like, yeah, and I have to do a try. it really seems strange. Let's see what it does. So the index, so we iterate over all the items, we find the item. If the compare function that we gave it between the item and the element is equal, then we break and we now have an index. But the element, but there could be two items that have that index. So I don't know if this would work. So we could, yeah, this is not going to work because there could be edge cases where that comparison function that just compares distances, they could be two of the same. And what, you're just going to remove the first one you find? Yeah, that's not correct. Let's try it anyways. I'm curious. Maybe I'm getting something wrong, but I don't think it's correct. Yeah, I mean it's not correct. So cool. All right. No more messages. How are we doing for viewers? Not many, but fair enough. Yeah, let's not do this. Because work queue doesn't even have. I could add. That seems. Yeah, there's remove. Pop the hardest element of the queue, null if empty. Okay, well there is remove index, so we can. This is just going to increase the runtime so much because I have to search for the index. This is strange. I don't actually know what to do here. It's the same order as iterator, which is not necessarily priority order. Okay, well let's just do it. I mean we have to, anyways. So it's just going to be linear search. That's terrible, man. But then if it's linear search, then what we had, find short's index, which was also a linear search, just isn't that bad. Yeah, I feel like there's a lot of stuff missing from this priority queue implementation, to be honest. What does chat think? Nothing else in chat. Is that maybe that's what the context thing is for? So I want to figure this out. I'm missing a trick with context full comparators. So let's read this. So we have context 5342280. We have a queue. We have some context. We're going to add 0, 1, 2, 3, 4, 5, 6. And we're going to expect equal. So we're going to remove. The first one's going to be 6. 6, 0, 1, 2, 3, 4, 5, 6. Min heap. Okay. Okay, so I think we can use the context here to denote, to show that work distance thing that we had. Context less than, this context, yeah, it does the context instead of thing, and this is a point, so that will work. We update, but then when you update the context, yeah, that's my problem. When you update context, what happens? Update after remove queue update 1.1. I am not sure. Not sure about this one. Okay, let's try the context thing. Let's try the context. U32, that's fine. Context of wait. Yeah, so I mean, we're only using it, it's only being used on the comparison function. The comparison function would take in no, man, I'm so confused by this. This is definitely a solved problem though. Okay. Priority queue, how to update a node value. Remove the item you wish to update and modify item as desired and reinsert it at the back of the queue. Yeah. Use the priority queue and push elements each time you wish to update it, except the fact that you will have useless entries to the queue when popping the top value. Check if it contains up-to-date values. If not, ignore it and pop the next. Use set. It is also sorted so you are able to extract the greatest element in logarithmic time. Okay. I think you're right about the standard priority queue implementation. Yeah, let's actually search for Dijkstra's algorithm. How to update priority queue. Yeah, because this is really what we want to do. Dijkstra using priority queue of EST. Okay. Update weight of v, i.e. do dist equals this is okay. Let's just look at this, the JavaScript implementation. We have a graph, yep, and then we have the priority queue on queue and queue. This is empty. So the shortest path, we on queue that, the distance of source 0. Priority queue.doQueue. We on queue it. Yeah, we on queue. Oh, that's not great implementation, is it? Because we have this here, then we go the adjacent nodes. But why can you just on queue? What happens to the original one? It just seems like in here it disappears. So yeah, I mean, you update the work distance, right? Wait, they have a v as well, which is the index. On queue element, the element sort by that. I hate this, bro. I hate it. How to update a key in priority queue, log in time in Dijkstra's algorithm. I have been working on Dijkstra's algorithm for the past 1 week, and I've running code. It is an array for computation, find main function, blah blah blah. But if a particular vertex exists in the heap, then distance might be updated taking into account distance of the min node. Now my question is, how do I update a particular element to heap and log n time? We cannot find an element in O1 time, right? In my naive implementation, it would be On. Yeah. Okay. I'm aware of two-based approach situation. Whenever you visit the neighbors of a vertex, insert them into the heap, no matter if they are in the heap or not. Then, when you get the vertex with smallest distance from the heap, check if it's already been moved from the heap before. If it has, then remove this one too and continue, otherwise mark it as removed. Ah. Note that the first approach would take a total runtime of e plus v times log n, as there can be at most O(n) elements per queue. Log e is still the same as log v in big O notation, by the way. Okay, so we have to mark them as removed and just ignore them and push. Okay. Alright, I think I'm happy with that. I think I could definitely do that. So basically, when we do a remove, we can check. Okay. All right. Okay. We're gonna have to update a little bit more here. Let's marked all. Now we should get a lot of errors, but we're not getting a lot of errors because the LSP is being a bit silly, I think. Where are my errors? Give me some errors. You won't compile. Yeah, so it's not giving me errors. Okay. Dot marked equals false. Okay. 2, run the macro again, run the macro twice, like that. Okay. Edge. Oh no, those are edges. Whoops. Should not do that there. Okay. Should do this 8 times. Like so. Does it compile? Yeah, good. Expect 18, found 17. Oh, that's that. Yeah, that's what I wanted from before. When we're updating the neighbor, then we go neighbor at the pointer dot mark equals true. And if at any point we go here, we go if the closest node that we removed, if closest node dot marked, if it's marked, we continue. Okay, expected 9999 found 17. Oh no, come on, what's going on? I will figure this out. I will, oh, it's okay. We'll figure it out. Let's go closest node dot label. Okay. Oh, we need a new line, otherwise it's not very legible. Okay. ACFGEH. I need to set it as marked, and then I need to actually work q.append. Add even. Neighbor. And as long as the add doesn't do any sort of checks, yeah, add and check, self, sift up the items, yeah. Then we should be good, because it's updated that distance, it does the sift up, then it is great, I think. Still nothing, same as before, you see, even though we queue the neighbor. Oh, we queue it, then we mark it as, yeah, I think, yeah, that part is, oh no, we have to then clone the neighbor, otherwise we're just changing the pointer, that's not good. Yeah, no, that's not good, because they're pointers, so updating one is going to change the other. Oh, that is terrible. Dug myself in such a hole. dug myself into a huge hole with this thing. I would have to change them to be actual nodes. Can I change them to be real actual nodes? What would that do differently? Node. We're changing the underlying thing. Work distance, yep. Yeah, it's tricky. It's tricky. Because you want to. Yeah, you want to update the distance, but you definitely don't want to. To be doing. Let's go back. Yeah, we can't even use this marked approach that we had just done. So that leaves us with that second approach that we had here. I suggest two problems. Use the priority queue and push elements each time you'd like to update it. Accept the fact that there'll be useless item in the queue and pop in the top item. Check if it contains the update value. If not, ignore it. You designed by top programmers, you set. It would have been a lot clearer if programs mentioned this fact. Thanks for pointing this out. Yeah, it can't be pointers. So it can't be pointers. We're gonna just insert nodes, and when we're gonna unqueue the nodes, they're gonna all have very big distances. They're all gonna have very big distances. Okay, look, let's start with some imperfect code. So if node.label, actually if node is equal to the source, then we continue. Then we change some sort of work distance. Do we change some work distance? I mean, do we even need to push in nodes? Like, we could use that context thing to do. No. To just have values and not actually use the node in the priority queue. But okay, we're down this road. And that's how it goes. We're gonna push in node. So node.star. This should make a copy of it because it's passed by value now and not by ref. Then what we're going to do is source.work distance is still 0, so we're going to try work queue.add. Oh my god, I've pressed so many keys there. Source.star. Just to make sure, we can do source.star.work distance is 0, but I don't think that's needed. Okay. What we're then going to do is, just to make sure we're still here, add and push elements. Some accept the fact that you have useless the queues. When popping the top item, check if it contains the update value. If not, ignore it and pop next. When popping the top value, check if it contains the up-to-date value. Oh, but this is not going to have the marked approach as well. And let's do that. So still do that. Okay. And we're gonna go if close node dot marked, and we continue. It's a useless item, and yeah. We add, we update work. Yeah, so to update, we just have to suck it up and neighbor is edge dot out node closest node work distance plus. No, this doesn't work. Does it work? Oh no, I think it does work because I can then say, no, I can't. Bro, I'm so confused. No. Okay, I'm just completely misunderstanding the problem. And what I'm doing is just wrong. What I'm doing is just straight up wrong. I would need more state, I would need something else, I would definitely need a whiteboard. I mean, could it be the case that we just never actually care about the underlying nodes? I mean, I just need a dictionary for the work distances, and we could find, when we do the closest node, we need to find its out edges. Closest distance, out edges, work distance. Yeah, no, it's kind of needed, isn't it? So yeah, let's. Oh, this is terrible. I hate it so much. Really just not having a fun time, my guys. Try work q dot put, because it's changed the underlying pointer. I mean, now I just need to resift. Peak remove, no remove, index count, sift down, target index, ensure total capacity, reset, iterated dump. We remove when we add. Yeah, I mean, this isn't quite, doesn't look like it's quite built for arbitrary types. Well, I think most likely I'm just misunderstanding things. So when we add, we sift up. Yeah, we append it at the back of the queue and we sift up. What we need to, we would need to sift up based on the index that this is in the queue. Fortunately, we don't really know that. I think we have to take the L on this one, actually. We had an array list and that worked. And I mean, this is not good, like, at all. But it did work. And, you know, I think I'm being silly. I'm being way too dumb to figure this out right now. But I just don't think we need to put edges in, and I could do well with bringing my own in again, to be honest. Bring in the work queue again. Sad that I don't know. Yeah, I have that implementation that I think I showed last time. It would be good to use it again, but let's stay with this for now. And we would do the advent of code. We'll actually do the advent of code problem. But I'm gonna take a little break. I will be right back. What do I put on in the meantime? I mean, what could you guys look at? Let's think. Screen Windows XP screen saver. Let's go online. Oh, there we go. Gonna turn the camera off. I'm just gonna mute. See you guys in a second. Hello, 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 welcome back. Just had some food, some scran. We have best views on something here. Well, thank you, but no thank you. Okay, so we finished off a little bit motivated, but we do have Dijkstra's algorithm implemented, which means we can actually do the admin of code. So I'm not going to look at chat. I am going to go to the admin of code here, and this is going to be YouTube VOD as well. So I'm going to post on YouTube. So, all right. So we're at day 17. I'm recording this one in a little bit of a different way. This is live streamed as well at the same time. But let's go. So we have a crucible. The lava starts flying rapidly onto the production, blah, blah, blah. You land near the gradually filling pool of lava at the base of your lava fall. Lava ducts will eventually carry the lava through the city, but to make use of it immediately, elves are loading it into large crucibles on wheels. The crucibles are top heavy and pushed by hand. Unfortunately, the crucibles become very difficult to steer at high speeds, and so it can be hard to go in a straight line for very long. The desert island, the machine part it needs as soon as possible. You'll need to find blah blah blah. To do this, you need to minimize heat loss while choosing a route. That doesn't require the crucible to go in a straight line for too long. Fortunately, the elves here have a map that shows you the traffic. So you can only move three and a bit. And I have done a little bit of thinking about this problem already. I've implemented Dijkstra's in Zig. So yeah, it's a graph problem. So as you can see, we can only move 3 in a row. And then the output is going to be 102. Because we want to get from the top left to the bottom right. And what else is there? Each block, okay, because it is difficult to keep top heavy crucible going in a straight line, it can move at most three blocks in a single direction before it must turn 90 degrees left or right. Crucible also can't reverse direction after entering each city block. It may only turn left, continuing straight, or turn right. So it can continue straight, if need be. Or does it 100% have to change direction? Okay, yeah, it says in a single direction before it must turn 90 degrees left or right. The crucible also can't reverse direction, can't go backwards. After entering each city block, it may only turn left, continue straight, or turn right. So that kind of conflicts with that instruction there. It can go left, forward, or right. Okay. So, if I'm understanding this problem correctly, we can't make a direct graph from this here. We have to make a special graph. We have to take each one and go right, bottom, whatever. We go from here to the right. We create an edge there. So we the vertices are going to be vertices or edges. I think an edge is what connects. Yeah. So we make an edge between here and here, between here and there. And between here and there. We do the same going downwards. We don't do it going backwards. But I don't think that would be an issue if we did. The reason is I don't think it will ever be the shortest path to go forward 3, back 1, and then up. it will never be faster to reverse, I think. So we can actually not worry about that, I think. Okay, let's construct the graph. I've actually done a little bit of work here, and I have implementation of dexterous. It's all working, it's very nice. It's not quite the most optimal. I actually have a stream where I did this, but yeah, I'm using an array list instead of a priority queue, because I could not get the standard library priority queue to really work for this case, because I need to update distances. It was a little bit tricky. So I've just stuck with this for now. Okay, let's make it day 17. 17, state 17.zig. Let's just copy this here. Yeah, there we go. And we are going to need the graph stuff a lot as well. Anyways, day 17. 17. And 17 there as well. Okay, let's get this example. Day 17. Zig run main. That should just do nothing. Yep, it does nothing. Okay, so we're going to go through the grid. We're going to be constructing some nodes. I also need to make a couple of these public, and then make dexterous public as well. I think that's it. Const graph is equal to import / graph / graph.zig. Does that give me autocomplete? It does. Nice. Okay, so we have edge, node, and then the graph. Cool. So what we're going to do is we're going to iterate through it for 0.input.length I for 0.input 0.length j, and yeah, we're going to create some edges. So first of all, we're going to go const node equals graph.node. Just going to have a label. The label is going to be, what can the label be? We could make it, how do I convert zig usize to char? Oh, I just, I plus. What was it? Standard.char. Wait, this does not look like zig. This looks like Rust. Yeah, this is. Have an A. Oh, it doesn't matter. Let's just not get too bogged down. Hopefully, we don't even need that label thing. Which is 0. We're going to use that later for dexterous. And the out edges is equal to just fine for now. Okay. Now what we're gonna have to do is we're gonna have to go up, left, down, right. So we need our checks, right? Our boundary checks. If I is bigger than 0. Then yeah, we're gonna connect. Oh wait, I need pointers actually. 'Cause I need to make a full graph, so I can create all the nodes. Right, I can create all the nodes no, wait, hold on. I'm still a bit confused by some of this. Okay, choosing a route that doesn't require the crucible to go in a straight line for too long. Fortunately, they also have a map. Each city block is marked by a single digit that represents the amount of heat loss. Okay. So yeah, you definitely can't just go in a straight line multiple times. I can't just continue down there, I have to turn. So the point being, how do I restrict this in a graph? Alright, so let's get another canvas here. How would I change this to be just a simple graph problem that I can run Dijkstra's on? So if I have node, 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 I can go this, this. So you'd have this, 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 but not all the way to there. But if you did this, 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 then you could go there. But it's about kind of accessibility, because what is actually not possible but would be in this graph is you can't go here and then back over to there, because you're now moving forward in a straight line. So how do you add the restriction such that you can't do that? Purely by making a graph. It has to be in the construction, right? It feels like you don't want to mess with the pathfinding algorithms. Is there anything wrong with my assumptions at the beginning to connect this to that, to this, to this? Maybe I need a different node, a different edge with the same distance for whether you're coming in sideways or not. So if I, let's say green. Okay. Instead of going to that one, I go here. Right? If I go in a straight line, I go through there. So I have the horizontals and verticals connecting different things. So I like to have a sub node. And then this node here only connects up and down. So it could go, I think I'm onto something there actually. You can go there. And then that's the turn, that's fine. But then I would also need another node here. Let's make these green. And it could not go left or right. It can only go up or down. I think that's it. I think we have it. I think, okay, I'm gonna try and explain it clearer. I think it works. Good, oh god, don't want that. we don't want that either. Okay. Okay. Let's say I have some green. Okay. I have horizontal nodes. Those horizontal nodes, I'm over here, top left. I can connect to here, to here, and to here. So let's make those. Oh, the thickness is so much here. Let's make it a little bit less. There we go. To here. And I can connect vertically. Let's do that in purple. In purple. Nope. Okay. Go sideways, and I'm also going to have a little node here. So now this horizontal node doesn't connect to this rightward node directly, but adjacent nodes could. If you go like this, and then you would have kind of the same setup over here for these nodes, where you go like this, like this, like this. But then these nodes here can connect to their cousins, like these over here. And the thing is that these purple nodes, so actually this here at the beginning is a purple node. Purple node connects to green nodes. Green nodes connect to purple nodes. So this would then connect to there, to there, and then to the right. I think I got it. So each thing has two like copies. So let's add a purple node. No, not this. A purple node twin here. This green node here can go down to its purple node on the bottom right, and it could also go down over here and over there, and then this purple node can once again connect to its green nodes. So really I am making almost two interweaving graphs, and then I think you're good. I think that's it. Yeah, that's strange. That's really strange. Yeah, but now it enforces the not going forward again, because you can't. Like, if I take 3 steps here, then I can only go down or up to my purple nodes, Okay, but how do we implement this in code? So for each x, y, so we create, let's call it H node, or H node, and a V node, so horizontal and vertical. H node and V node to create both of those. We create the whole kind of system of them. And we can keep them separate. And we can keep coordinates for them. Then after we create them, we can go, if we go for each H node, I have its coordinates, so get horizontally, I'm a horizontal, so I'm one of the green nodes. I can either go up or down. Go up, down, times 3, create edge. Okay. Now the annoying part, I guess, will be getting the pointers for the V nodes. So I think what we'll have to do is we'll have to have a map of V, like a vertical node map that has the coordinates and the well, the pointer to the node. And we'll need the same for horizontal, and then we do this. Damn. Okay, I think this is right, or at least I think I'm onto something. And I'm really, really happy, because this type of problem would usually really consume me. But yeah, I think that's it. You create this kind of like lattice structure. I mean, I think it will work. Very, very exciting. I think just gonna stare at it for a bit longer. Okay. Let's code. So, first of all, let's create nodes. Let's create var horizontal h map, because we can interpret our values equals standard equals import from standard library, and dot auto hash map between 3, 8, which is going to be coordinates, and pointer to graph.node. And I do have chord functions, so many coordinate functions that I've just copied like this. There we go. And then we also need a vertical map, vertical node. Let's call it just say v node there, h node, and let's go const coordinate equal c equals chord of, so I is, yeah, it's got to be ji. It's actually the wrong way around. So instead of j, let's just say x. Instead of this, say y, so we're a bit more familiar. And then we're going to go h_map dot put. And that can throw an error. So we're going to put c, and then we're going to put we need to create these with an allocator, otherwise it's not going to work. Because they would be released from the stack. Or do you need to? Do you need to? Because you want to create just a pool of nodes. Yeah. Okay. Standard.heap.page allocator. We need to create them. Graph.node. I mean, if we create and then the problem is we could put in values here, right? But I want to put in pointers because then you can use them straight away. So yeah, I think you're going to need to create them like const v_node equals page allocator. Actually, let's just call you allocator dot create. Not you there. We're going to create node and v_node dot start dot. You do know what your type is. Oh, graph.node. v_node dot start dot. Let's start initializing some stuff. The work distance is 0. The label is going to be just v_node, and the edges undefined. And then that's going to be h. You're going to be v. Okay. Good. Now we have both of these. We have two maps, a horizontal and vertical map, for each one. What did I say on over here? We create each one, and for each vertical node go up or down. So let's say var hmap iter, which is hmap dot iterator. Creates an iterator of the initial map. The iterator is invalidated if the map is modified. It's fine. While h_map next, we're gonna have entry.q. So this is gonna be, let's say c is equal to that, and let's say hmap h node is equal to entry.value pointer dot yeah, that one, the h node pointer. Okay, now all we want to do, we actually want to decode this to be function from coordinates. Oh, we could add x and y to the nodes. Add x and y to the nodes. Yeah. Or maybe not. Let's keep it separate. Function from coordinates c, which is a u I 1 to 8. It returns. How do I return tuple? Sig tuple. Tuple. Tuples. Anonymous structs can be created in reference to tuples, yeah. usize. Okay, so const the x equals to as usize c shifted to the right 64 times, and const y equals that truncate. This function truncates bits from an integer type, resulting in a smaller same sized integer. Truncate just c, and return x, y. Okay. Something from coordinates c const x equals that, and that should give me, oh, unknown. So again, the tuples. Oh, please don't copy strike me. Yeah, that does work. Oh, actually, let's just keep things simple. Struct coord x usize y usize u return coordinates is equal to struct. There we go. Let's return dot x equals x dot y equals y. Map c, map underscore c, and then now this is going to be the actual coordinate. So we need to go up and down. We actually do want some restrictions here though. So we want to go, this is horizontal, so we go up. So if we go up, we need to go var y equals c dot y, and we need to go while I'm gonna go var counter equals 3. While counter is bigger than or equal to 0, is bigger than 0. It's going to go 3, 2, 1, and y is smaller. No, and y is bigger than or equal to 0. Oh, this is going to cause a little bit of an overflow. Okay, let's just go while counter is bigger than 0. Counter minus or equal 1. Okay, so we're going to go. We're going to have to create an edge. Const edge equals try allocator dot create graph dot edge. Edge dot out the end node is going to be equal to h underscore node. So that's where it goes from, and it's going to go to let's go edge out coordinate, which is coordinate from my x, which is going to be c dot x, and this is going to be y, the changing y. Y can at most be 0. So we're actually going to need to go -1, but if we do -1, we could very much be on an edge. Let's figure that logic out in a sec. And we go const out node, which is equal to v underscore map dot get the key, which edge out coordinate dot question mark has to be defined. Edge dot out node equals out underscore node, and that's it. We keep going down the counter, but we need to do some checks. Right, so first of all, if y is not equal to 0, then do this, and then we have an extra check even. What's going on here? End of file. I think the LSP is just being strange. Okay. If y is not equal to 0, then well, actually y is bigger than 0. Then we continue. We're going to keep taking away y at the end. And, well, actually, we could do it inside here, no? We go if y is equal to 0, then we break out of the loop, and then, yeah, that solves the problem. Okay, let's just go back in so the LSP can start behaving again. Local variables now mutated, are you sure? It goes y minus minus, like so. Minus or equal 1. Good. We're going to need to do the same thing going the other way. Same thing here. It's duplicate code, quite a bit of it, but okay, we go up, and because we're going up, if y is equal to input dot length minus 1, we break, and then we also go count is equal to 3 again. Okay, I think this creates the horizontal ones. Now we're gonna need, oh, actually I misspelled that. This should be the V node. VMap iterator. H underscore map underscore iter, which is V underscore over V underscore map underscore iterator. Okay. Find coordinate, and it goes through V, actually gets H here and H here. Wait, so I'm doing this wrong. It's actually easier to just do H map. So horizontal map, they can go up and down, which is what this does. Let's change it now to go vertically. H node, V node from coordinate, and then we change this to X, C dot X. If X is 0, X, C dot Y. We go on the horizontal map, we allocate, it's going to be V node, out node, X minus or equal to 1, X, and this is going to be the same static one, C dot X, V underscore, and then C plus or equal to 1. It's not input length minus 1, it's input 0, length minus 1. And I think this creates our funny lattice. I hope. Okay, anytime errors. Okay, yeah, that's init, right? Okay, what else do we have? Incompatible types, comtime int for C. C plus 3 equal 1, C plus 3 equal 1, where? Wait, what was it on about? 126 C plus or equal to 1. Oh, this is X plus or equal to 1. What else do we have? Expected type view size found U. Okay, yeah, I mean, we're shifting it down. Do I need a... So we shift it down, then we truncate, maybe? So it's actually going to be at truncate, like so. Okay, that runs. No assurance that it's correct. But I think our logic is sound, which is nice. I've created the edges, but I'm not actually attaching them. So for each of these nodes, I'm going to need some out edges. Edge. Yeah, and I casually just don't do anything with that edge. So so we're going to go const, actually var edge array, which is try allocator.alloc. We've just I keep remembering that we just never free memory. We're just not freeing memory. Pointer to graph.edge, and it's going to be of 3. Let's actually replace that 3 with const max straight line move, which is 3. Max straight line move, max straight line move, max straight line move, max straight line move, 3, 3, reset here, max straight line move. Okay. And what we can do is we can actually just depend on counter because yeah. Edge array. Up. Oh no, it's going to be 6. Oh, so I have to actually times it by 2. So it's going to be at counter is equal to edge. And then very similarly here, max plus counter edge. Do you compile? Do you compile? Compiles, but it crashes. Why? Index out of bounds 6, 6. So the counter at this point could be 3. 3, 3, yeah. No, 0, wait. There. What about here? Can I not go? Because it goes 3. I think it should crash there as well. I think I just have to minus one here. Okay. Yeah, it was off by 1. Okay. And I need to do the same here down there. Down here. And then for you it's just this, but for down here we do max edge plus counter. Yeah, cool. Okay. That all runs. We're all good, I think. I hope we're all good. Let's just check. So let's check the horizontal one here. And let's just print. Let's go with any dot slash ed the ish node star. Wait, what? Oh, maybe just this. Oh no! Errors. Hate these. Address violation. Oh, yeah, okay, I get it. Because after I do all that, I still need to go h_node dot star dot out edges equals edge underscore array. Edge array, oh, it is actually not a bunch of pointers. This is very much a bunch of pointers. Creates, appends. Does this. Oh, I don't need to. Oh, yeah. So here I can actually go edge in underscore node dot. Oh, come on, LSB, work with me. Graph dot edge dot in node h node dot out node. Oh, the distance. Didn't even think of that. It's kind of important. Distance is actually a good question. Distance from here to the next one is what? So, I mean, so for at 2, each city block is marked single digit, the amount of heat loss if the crucible enters that block. So distance from here, it starts at 2. So what we should do is we should do from here to there is 4. And we should have like the beginning at Yeah, we should add that at the beginning. We'll do that in just a sec after we finish this. Distance 0, but we need to fix that. There we go. Yep. Yep. H node, that's going to be V node now. And that can go away. Const edge, yeah, that can go away. V node, yeah, okay. Do you compile and run? You do not compile and run. You don't like it. Let's get rid of you. It does work, kind of. It does something weird. But maybe, well, might just be kind of strange, as in it's strange to print. Maybe, what if I just do dot label? Edge dot length. Or actually, just, yeah, length. 6, good, that's what we want. Okay. I think that's all correct. Now we're gonna do the distances, which is actually really easy, I think. Distances are gonna be the input at y, and then c dot x take away 0, because that's the because it comes in ASCII code, so we need to do that there. A lot of repeated code that we will definitely change for the better, but not yet. Okay. Is that all still good? That's all still good. Well, I mean, what is left to do? I mean, we need to call Deichers with the top left and top right. So let's go const start equals h. Oh, actually, we kind of have to do 2 passes, right? Because we can either go to the right or we can go down on the very first one. Because it's an example, let's select a vertical node that can go to the right. So let's go v underscore map.get. The key is going to be coordinates 0, 0. Const end is equal to, and it's going to finish so it's going to be another vertical node. So I think we're going to have to do a few passes here though, because we're not quite sure of certain stuff. The x is going to be input 0.length minus 1, input dot length minus 1 dot this, graph dot Deichers. Oh, allocate. Oh, I need graph. Graph equals graph dot sag graph dot graph nodes. Yeah, we're going to need to add all the nodes into this. Const node all nodes equals try allocator dot alloc. What is it? Oh, we can do it. Dot count times 2, and it's going to be of pointers to graph dot nodes. And now we can probably do this Yeah, I mean, I can probably do it in the loop, but okay. Yeah, let's do it in the loop, and let's just do. So I mean, it's going to be input dot length times input 0 dot length times by 2. And let's do index equals 0. View size doesn't do it there. It does actually do it there, yeah. So let's go v underscore node. Actually, all nodes at index equals v node. Index plus or equal 1. Same thing here. For that would have been big trouble. Like this. All nodes. And then dextrose, the allocator, like G for graph, the source, start and end, const part 1, try part 1, print part 1, okay. Okay, didn't work. Why? No address available for neighbor edge.out node. So when we construct it, we have edge out node equals out node. Out node equals out node. Out node equals out node, out node, out node. Yeah. Out node, that is a pointer. Okay. I think that should work. Doesn't though. Let's just do g.nodes at 0 dot. What's it concerned about? It's actually concerned at specific edges. Let's just do this one to start with. Oh, that's not right. That's really not correct, isn't it? Out edges for this, for the very first one is that many. That's not right. Not right. Anything in the chat? I haven't looked at chat in a long time. Wow, okay, well, we have a lot of chats. Sorry guys, I haven't really been paying much attention to chats at all. Fortress 2 came out. Okay. Hi, good work. Declaration of HNode. Why you don't guide others as to what's going on. Yeah, that's a good point. Hello, everyone on Twitch. Hi, from when are you using Zig? A little while. I did the admin of code to learn Zig, but I knew a little bit. I'd say about a year. I've been doing some bits of Zig. It's obviously not what I do for like my day job, but I do it from time to time. Hello, how's your day going? What are you developing? Yeah, I'm doing some admin of code stuff. It's like a coding problem about well, yeah, you just get given like some instructions. You have to figure out a way to model it and, you know, construct stuff. It's that type of thing. Okay. I'll try and look at chat a little bit more often. Okay, what we have here is something a bit strange, where I think this just cannot be the length of out edges, because that would be way too many. And I wonder, let's print, I wonder if we can print the address of H node. H node is still a pointer, so maybe we can print the address. And I wonder if we have some sort of address. Zig address print pointer address. Zig by example pointers. Value pointer. Doesn't like it. Does not like it. General protection exception, because it tries to print stuff that isn't really there. Why does it go out edges is equal to anything, to be honest? Just undefined. And that's the very, very first one. Okay, let's test equals h underscore h map dot anything in chat? Anything in chat? No. I'm just gonna try and I'm really not, the LSP is not liking me today. Like at all. V underscore map dot get. It likes it now. Well, this. I wanted this. That's the test dot start dot out edges dot length of out edges. Yeah. It's just too much. Like it really isn't that large. It just can't be. So I don't know what it's doing, but it seems to just be pushing on the same one. Also, that's just so many edges. There's no way it's actually that many. Right? Feels like it can't be that many. Yep. And I mean, we're not crashing up there. We're not crashing in here. Print, let's just do this here. Sanity check. Yeah, okay, that's all good. Sanity check goes down to 1. Counter gets reset. Let's counter bigger than 1. minus 3 equal 1. And we continue. The edge is graph.edge. Yeah. The edge array is allocated there. And then it goes in here, out edges. Don't actually see what's wrong, to be honest. Sanity check again. Let's try that. 6. Yeah, that's fine. So I really wonder why it's giving me this many. It just can't be this many. For g node 0 dot out edges e prints question mark. I feel like something is being really strange. No, look how many there are. That can't be right. This cannot be right. That's so strange. So strange. Why does our edges just have so many? What if we go all nodes 0 dots out edges? Same thing. It feels like somehow it's all being polluted. It feels like this array inside there is just like, how does it get so massive? Massive straight line move is 3. Okay, let's go through all nodes and sprint let's do that. Okay, so it's every other one, so that actually does help. That means that there's an error in a specific part of the code, and is it specific to vnode? So the vnode are being very silly, but this here is being better. And now I'm starting to regret duplicating so much code. But still, should be able to figure it out. We allocate max straight line move times 2 and same ones. And edge array, counter minus 1 is equal to edge, this plus that. Yep. And then it's going H. Oh yeah, okay, well, there's the error. I mean, there we go. That was it. Some weird, just forgot to create certain pointers. Okay, now it's all correct. And now, okay, hold on. No, this is good, Now we can hopefully just go from start to end. Do have a lot of print statements still. Back and go. Where's the next one? Next one's there. No address exception on what? Is it that I didn't set a work distance for up here? But I did for both. And it's crashing in. Let's see this error. Okay. It's going alternate. Okay. Let's step up our debugging a little bit. Let's step up our debugging, and instead of this, I need to construct a string somehow. Sig append strings. How to can add two string literals. Okay, so you can just do that. Okay, that's nice. vnode dash plus plus on x, which is going to be, well, x plus 0 plus plus y plus the binary 0. Okay. Is that all good? Expected indexable found as u8 as u8. Ooh. Oh no. Yeah, that's, hold on. Doing the wrong thing. And that could be a few characters actually. Oh, I hate it. Okay. Okay, let's go back here. Let's see how much of Dijkstra's it gets done before it crashes. So it goes out on the alternate path. Alternate path being here, edge.distance. Oh my god, I'm getting so many like Lua errors with the Zig LSP. Like something is just not working correctly. Let's just write test over here. Just see how many times it runs. If it crashes on the very first one, then we've set something up wrong. Yeah. Crashes right on the first one. So, yeah. And it crashes because, what's the error? General protection exception, no address for the work distance. Neighbor. Well, actually, neighbor. Let's print neighbor, see where exactly it goes. Out edges equals. Okay. Let's print the label. Which one do you do first? To see if I can locate that part code. It really does not like it. What if I go ahead and print edge dot just distance? Not you. Distance is okay. Distance not initialized. No zero initialization, Zig. You're slacking. You're actually slacking. distance is initialized there, and there, and there, and there. What are you yapping about then? Yeah, it's initialized everywhere. Distance, edge.distance. Yep. That works too. General protection. No, that's that further down the line. Edge, graph the edge distance again. It's yapping. It's yapping. The program's yapping right now. I get a general protected address from what? What is... Because I'm then saying that edge is... Maybe I can go straight in like this. Maybe there's something that some unknown behavior that I don't know about. So then we define it straight on the edge array, which is heap allocated. Which is heap allocated, and then maybe what's going on? Edge. That's right, yeah. Oh, it's yapping again. Program's yapping. Okay, so let's just go print test g.nodes at 0.outEdge 0.distance. Did you just crash straight away? Oh, it's yapping. Program's actually yapping right now. Why does it set it there and then it doesn't set it anywhere else? Like... pure waffle. It's just waffling right now. This is really weird behavior. Really strange behavior. Because obviously this is just the address to random position in memory. Yeah, we faced this problem before. Well, similar problem. Let's go back. Back. Okay. Edge. I mean, the other thing I can think of is doing something kind of ugly. Allocator.create, but I need to understand these memory errors. I feel like I don't understand them properly, so I can't debug it properly. So I should just do like a stream, a video, anything where I just go through and do stuff like this just to see what's going on. Okay, we have that there. I think we do the same for this. Does anything change here? I think not. Yeah. And then for the X, it does change a bit. So this goes V node, this goes C dot Y, X, this. All right. And I mean, yeah, it is an edge array, but you're complaining when it's not waffling, actually waffling right now. Oh, don't want this. Oh, was that one of the problems? Ooh, maybe. Dot star there. Compiler agrees. Compiler's still complaining. Compiler still goes on about something. 0 dot out edges, 0 dot distance. Print that. Okay, so none of what I just did, basically. What we had was fine. Is it this? Is it? Let's print edge array at 0. Oh, come on, where was I? Dot distance. And let's then print h underscore node dot star dot out edges at 0 dot distance. And it's all good. And it is all fine. Let's print over here. Maybe. Let's change the out edges to be pointed to an array. I think this is going to break the test cases. Oops. Closest node dot star dot out edges. Wait, what? Dot star. Well, okay, that didn't die. So I think that worked. Actually not entirely sure why, but it did. Start at 0 dot distance 7. And I mean, now it's waffling again. Let's try and say print running dot dot dot, because we want to see how many times it goes around our dexterous algorithm loop. Running, runs. That seems like the correct amount of times. Runs the correct amount of times. What work distance, print updating work distance, neighbor.star.work distance. Oh, it stops after a while. It stops after a while. It goes 7, 8, 7, 9, 7, 14, 13. Oh, wait, I think I made a mistake here. This, yeah, this isn't it. I can't, yeah, because they're not single digits, so that doesn't work. Okay. Zig. Oh no, they are single digits though. They are single digits, yeah. So that should work. Print edge distance. Edge.distance. Let's run that. Edge distance, yep. Closest. I think, yeah, I mean, what is going on right now? So we set that to 909, we set the source dot work distance to 0, it finds the closest, finds the closest one, then it dies. Ordered remove from the closest node index, found it up there, where the work distance is less than, yeah, that's fine. That is interesting. That is interesting. At one point it just stops. So I do wonder what's going on there. Print. Oh wait, my distances are wrong. I realize, but I don't think that's the case. That's the issue. Yeah, I just said distance to go from here to there, but we need to actually count the distances beforehand as well. So going from here to 4 should count 4. We're going from here to 4 to 1. That should be 5. Well, 2 plus 4 plus 5, but yeah, that, I mean, that could cause some issues. So let's accumulated distance usize 0. Anything on the chat? Anyone asking any questions? No. Accumulated distance. Let's just go accumulated distance plus or equal to input at y c dot x take away 0. Accumulated distance. We're gonna have to do this 4 times. Really, okay. The next step would actually be to kind of refactor the code a bit because it's looking so janky right now. Well, accumulated distance, size 0. plus or equal. I don't need to reset it here as well. Accumulate distance 0. And up here too. Okay. And then here. Same as over there. Accumulated distance equal to this. Let's reduce the input a lot. You know, let's just have this many. It's funny it doesn't work with that. Print E1 and then E2 start dot out edges at 0 dot star at 0 dot distance. Yanked that. This, there we go. That's the start, like distances. First one is just that, so you know that just can't be good. And I wonder if that's part of the reason it's not working very well. Because I mean, we have edge array. We have edge array counter -1 equals edge distance accumulated distance. Print distance accumulated distance. There we are. Accumulated this. Yep. There it is. It's all good. And out node, that will point. That's a pointer. That's all good. Edge array counter -1. Show line moves. It's going to be 6. It's going to be 6 there. 3. So -1, 5. Yep. It feels like it should be fine. Print E1. Let's do a very, very similar thing here. V underscore node dot star. Node dot star. Let's do a gur beforehand there. Okay, it's dying a little bit already. And it's dying a little bit because why? Because oh, come on. Real one. Let's go edge array at 0. Oh, the real one is bad as well. It's not just the other one. So the real one is breaking. Interesting. Strange, isn't it? Very strange. Yeah, I really haven't got this code done very well. So that's probably part of it, to be honest. Debugging. Talking about debugging, a debugger would be great here. Okay, last bit before I actually, call it a day and we can continue later. Filling index counter -1. Filling index 2. Okay, well, I think we found the problem. Here goes. Filling index. Wait, top. Let's do top. Let's do bottom. Top. Wait, and then go straight to bottom? No. Wait, where the hell is counter defined? Here. So it goes 3. Oh, wait. Yeah, no, we don't want to alloc this many straight away. Right, because if we're at the edge, then we're not actually going to fill up this many. It's going to be tons of other stuff. Okay, so basically my code is just bad, and I didn't think about this all the way through, because if we're at the edge, we're not actually going to have 6 edges going either way. We're going to have something a bit more constrained. So I'm going to fix that. Yeah, I'll fix that. Cool. I'm going to end the stream now. And I'll continue this later. Probably do it offline though. Yeah, thanks for everyone who tuned in. And yeah, catch you in the next one.